So if you are doing a line integral of a vector field f, and your line integral is done along an oriented closed curve, emphasizing the closed here, then our line integral formula that we were working with before, the integral over the curve of f dot t hat ds, we call that the circulation of the vector field. It measures the tendency of something to flow in the direction of that oriented curve c. When we're doing a line integral over a closed curve, you will often see this notation where we put a circle around the center of the integral sign. That indicates that C is a closed curve and that we're integrating not just on some curve that may go from one point to another, but actually a closed curve. So the line integral will include this notation. Closed curves versus not closed curves, you can think of a closed curve as having a definite inside and outside. So like a circle and an ellipse, those are closed curves. There's an inside and an outside here. Not closed would be something like a piece of a parabola. There's just one side of the curve or the other. There's not actually a closed off inside and outside region for those. So we'll still be calculating these as we did our previous line integrals over vector fields, but we'll actually be considering that to be the circulation and looking at and interpreting it as circulation in this video when we do our examples. Let's look at our first example here. We want to calculate the circulation of the vector field negative y comma x along the circle of radius 2. We're centered at the origin and we are oriented counterclockwise traveling on that circle. I'm going to go ahead and use the differential notation. Remember, this integral over the closed curve f dot tds is the same as this integral over the closed curve f dot dr, and that's the same as the integral of mdx plus ndy. I'm going to think of it in terms of mdx plus ndy. Remember, the first thing you want to do is parameterize your curve. So we'll go ahead and think about the circle with radius 2 centered at the origin, oriented counterclockwise. If we write that as r of t, I can write that as 2 cosine of t comma 2 sine of t. So that is our parameterization of that. And if I'm only going around once all the way, then we'll also go ahead and say that t must be from 0 to 2 pi here. Okay, so this is our parameterization with time domain here. And now we just want to write our integral mdx plus ndy over the curve. Let's go ahead and think of it. Now remember, we wrote this parameterization to say that this is what we'll consider x, and we'll consider this to be y. So when we write mdx and ndy, that's what we'll use. Now additionally, looking at our field here, we notice that m is negative y and n is x. Remember, it's always m comma n when we think of our vector field. So we'll go ahead and write this down. So m is equal to negative y, and if I know y is 2 sine t, then m is actually negative 2 sine of t. And if I know n is x from my vector field, and x I know from my parameterization is 2 cosine t, this is 2 cosine of t. So I know m and n in terms of t. Now I also need dx and dy, right? So if x is 2 cosine t, then dx is going to be, think about the derivative of 2 cosine t, that would be negative 2 sine of t dt. And if y is 2 sine of t, we need dy, so dy is 2 cosine of t dt. And if we go ahead and plug all that into our integral, then we will get that the circulation is equal to the integral from 0 to 2 pi. So now for mdx and ndy, notice they're both going to have a dt in them, so I'm just going to factor that out and put it at the end like we would normally see for an integral. So m dx is going to be negative 2 sine t times negative 2 sine t again, so that's going to be 4 sine squared t. And then the ndy part, so plus ndy, I have 2 cosine t and another 2 cosine t, so that's 4 cosine squared t. Factoring out the common dt's, I'm just going to write it at the end, dt. And now this should look like something that's pretty easy to do, right? This is just a Pythagorean identity. Sine squared t plus cosine squared t is 1, and I have 4 of those. So our integral here is actually going to become just from 0 to 2 pi, we're integrating 4 dt, and that's a really easy integral to do. We just get 4t, and we evaluate from 0 to 2 pi, which is also easy, right? So plugging in 2 pi, we would get 8 pi. Plugging in 0 minus, we would get 0. So we just get an answer of 8 pi here. So the circulation is measured as a positive 8 pi for our answer. If you look at this vector field and our parameterized curve, you can kind of get an idea of why that is, right? If I'm traveling one full rotation along this curve, this vector field is certainly pushing me that direction, right? It is pushing me in the positive direction that I am traveling, which was counterclockwise around this curve. So we get a decent amount of circulation. We get 8 pi circulation going around this curve here. We're going to now calculate the circulation of this different vector field on the exact same curve. So we're going to do the same r of t is going to be 2 cosine t, 2 sine t, because we are using the circle of radius 2 centered at the origin, and we're moving counterclockwise. And if we go once again, so we're still going to be using t 0 to 2 pi. So just doing a couple of similar examples so you can get sort of some practice and see simple examples of how circulation works, right? So I know that this is x and this is y, and remember in f, remember the first component is m and the second component is n. So now we just write down our m dx plus n dy. So in this case, m is x, and that's going to be 2 cosine of t. And n this time around is y in my vector field, and y is 2 sine of t. And we'll get the same dx and dy that we got last time because we're using the same curve, right? So dx here is going to be negative 2 sine of t dt, and dy is going to be 2 cosine of t dt. Okay, so we have everything we need, and now we just write our integral down and calculate that. So we'll get the integral, our circulation, will be from 0 to 2 pi. M dx, again, I'll factor out my dt and write it at the end. So I have 2 cosine t times negative 2 sine t. That's going to be negative 4 sine t cosine t. And then plus n dy, I have 2 sine t now times 2 cosine of t, so that would be plus 4 sine t cosine t. Integral of all that dt. And what you might see here is that negative 4 sine t cosine t and plus 4 sine t cosine t is going to give us 0, right? So actually our circulation is going to be the integral from 0 to 2 pi of 0 dt, and the integral of 0, no matter what we plug in for bounds, is just going to be 0. So we get an answer of 0 for the circulation for this one. Let's take a look at our vector field and see why that happens now. So we've just changed the vector field. We're still traveling counterclockwise around this circle of radius 2 one time, but this is now a radial vector field. All of the vectors are pointing out straight from the origin. In other words, if you look at any point on the circle, all of the vectors are pointing normal or straight out of the curve here. So in terms of how much is this vector pushing me around the curve at this point, well, it's not helping me around the curve any because it's pushing straight normal or orthogonal to the path that I'm trying to travel. So it doesn't actually assist us at all, and we get a circulation of 0. Looking finally, let's change our vector field one more time, and we'll do this with the same curve. So we're still along the curve of radius 2, centered at the origin, moving counterclockwise. So our parameterized curve is going to be 2 cosine t, 2 sine t, and also we're going to go from 0 to 2 pi, just like before. So our x and y are the same, 2 cosine t and 2 sine t, but now our vector field, our m is positive y and our n is negative x, so a little bit different than what we've done. Let's go ahead and write down what we would have. So m is y, and y is 2 sine t, and n is negative x, and x is 2 cosine t, so negative x would be negative 2 cosine t. Let's go ahead and write down our dx and dy. So same as before, if x is 2 cosine t, then dx is negative 2 sine t dt. And if y is 2 sine t, then dy is 2 cosine t dt. Again, we're just getting those from up here where x and y are. And now if we write down our integral, so our circulation is going to equal the integral from 0 to 2 pi of m dx, we get negative 4 sine squared t. And then n dy, I also get a negative 4 cosine squared t dt. So we get this integral, and now basically we have negative 4. If you factor out a negative 4, you would have that times sine squared t plus cosine squared t. In other words, negative 4 times 1. So this integral actually becomes the integral from 0 to 2 pi of negative 4 dt. And if we integrate that, then we'll get negative 4t. And then evaluating from 0 to 2 pi will be similar to what we got 2 examples ago, except it will be a different sign, right? So we get negative 8 pi minus 0, and that's going to give us negative 8 pi. And if we take a look at the vector field here, so again, same curve, same circle, radius 2, going counterclockwise, you'll notice we have a rotational field here with y negative x. So this field is actually fighting the direction that we want to go around the curve if we want to go counterclockwise. So it is providing some circulation, but this negative is actually telling us that it's providing that circulation against the flow of where we're trying to travel. So we get a circulation that is negative 8 pi in this case. Okay, everyone, hopefully this helps you setting up your M, N, P, X, Y, Z and doing your circulation around closed curves. Our next video in this line integral series is actually on integrals involving flux, so check that out. We'll see you in the next video.